Excellent. Okay, so big thank you to the organizers. And before I get started, I want to just tell you a little bit what a plan is. I was asked to talk about different analytic methods in the study of, say, rational integral points. So as a starting point, I chose in the first lecture to say a bit about vibration theorems. And a conjecture on split values of polynomials. So here I will overlap a little bit with what Cyril is going to do later, but I need it as a motivation to tell you one problem that I hope everyone is interested in. And then we will run into this conjecture. And then my plan is to present three very different approaches to how you can approach this conjecture with different analytic methods. So in the, say, second part or second lecture, roughly speaking, we will talk about an approach or some results from additive combinatorics. The goal of the lecture today is to explain what this conjecture is and how to formulate into a problem that you could apply these methods to. And next approach is a circle method approach. I hope that I have some time to indicate where they overlap and what the sort of different strengths are, or why one or the other you may want to use. And I hope that we will have then on Friday time to touch upon sieve methods. So each of the last three keywords that I've written on the board are really big, of course, really big areas in analytic number theory. And I will just touch upon each of them to illustrate how all of them can be used for that problem that I hope is going to be of interest to us. So the goal is mainly to indicate how at all to formulate it into a problem to which then one of the toolkit can apply. So I'm going to start now from the very beginning and start with the Hasse principle. So if you have some family of nice varieties, so say smooth, projective, geometrically integral, over a number field little k. Then we say that this family satisfies the Hasse principle if, for all element in the family, if you have local points everywhere, you have a k rational point. So we say Hasse principle holds for this family if for all members x in the family, the statement is true that if you have adelic points, then you also have a k rational point. And as we assumed that our varieties are, I think, even projective, this is just a product of local points, that is a product of all places of little k. And moreover, f satisfies weak approximation WA if for all members in a family which have local points everywhere, where the set of adelic points is not empty, the image of the diagonal map from the rational points into the adelic points is dense in a product topology. So this will for sure, I guess, come back a lot today, but I hope that this is something that we are all maybe interested in. Of course, you guess all know examples. So quadrics satisfy both the Hasse principle and weak approximation, the theorem of Hasse-Minkowski, or principal homogeneous spaces of semi-simple, simply connected linear algebraic groups, or also result that Emmanuel was mentioning yesterday. If you take a hypersurface and projective space, then the theorem of Birch that he was talking about also ensures that such hypersurfaces of low degree and large dimension satisfy both the Hasse principle and weak approximation. So there's large classes for which we know that these nice properties hold, but both of them can fail. And I'm just giving one example because this is also going to be, I think, in detail discussed later. So just one example, say, of Selmer, 1957. Say the cubic curve 3x cubed plus 4i cubed plus 5z cubed. 0 has local points everywhere, but no integer solution. Many examples for nice classes of varieties can be explained by some Brauer-Manin obstruction. So for many classes of varieties, we understand what is going wrong and why the local global principle does not hold. So many examples, many failures. So yesterday, learned the day before so much about the Brauer group in David Harari's course. So for here, let's say Brauer group of X is the second étale cohomology group of X, GM coefficients. Then you have a pairing between the Brauer group of X and the adelic points in X mapping to Q modulo Z, which I think is probably also going to be discussed today. Very good. So you will see this in detail as a pairing, which, yeah, you kind of pull back your local points and then make the local invariant maps and add them up. The point now is that there is a subset of the adelic points, the Brauer set, which is a set of all adelic points which paired with any element in the Brauer group map to 0 under this map. This is a subset of all adelic points. And the rational points, they sit inside here. And that way, the Brauer group can be an obstruction to the Hasse principle and weak approximation. So for example, you could have local points, but none of them survive this Brauer-Manin pairing. So yeah, then the next question is, when is this Brauer-Manin obstruction the only one? When can we make sure if we check this as well, we find points? And there's now a conjecture of Colliot-Helene, say conjecture 1 maybe. From 2002. And he came up with a class or conjecture and a class of varieties which behave nicely enough that you expect the Brauer-Manin obstruction to be the only one to Hasse principle and weak approximation. This statement is let X be a nice, smooth, geometrically integral projective variety, which is rationally connected. So for example, Fano varieties. And then the conjecture is that the rational points are dense in a Brauer-Manin set. So one approach to these conjectures is via some type of vibration theorems. So you may have the idea that you look at some large variety X, which comes with a morphism, say, to P1, and then you hope to deduce something on this conjecture when you understand the fibers, and then you want to move to the total space. So say typical formulation of a theorem that one would like to have is the following. you may start with some nice variety over some number field, and then assume that there is a dominant morphism let's call it f from x to p1 this rationally connected generic fiber, which implies that the whole space is rationally connected, and then would like to have a statement of the following type. So you have, say, this is x, and then this is p1, and f. And then you would like to deduce that if the fibers behave nicely, or almost all fibers behave nicely, so if they satisfy Collier-Tollean's conjecture, then the whole space does so. So you would like to say a statement which I call now A, abbreviated, if the smooth fibers of f in your vibration above rational points of P1, if they satisfy conjecture 1, then also the total space X satisfies conjecture 1. So you have some vibration, and maybe you understand the fibers, and then you understand the total space. It turns out that such a statement, such a vibration theorem, depends on what is called the rank of the vibration. The complexity of proving this is very much connected to the rank of f. And so I want to define now what this rank is, because it will also then measure the complexity when we throw analytic methods on it. So that's why I want to introduce what a rank of f is. So some of the, there's, most of the fibers, they are smooth, and there's some bad fibers. And bad fibers are fibers which are not split. And definition of split is, I guess, due to Alexei. No, okay. Okay. But a previous item. So we call a variety split. If it contains a geometrically integral open subset. So if you are geometrically integral yourself, then you are split, or all the smooth fibers are split, so they are all good. Or if you are, say, two lines which are defined, each of them over the ground field little k, then this is also split, because you can throw away one of the components, and the rest is geometrically integral. But what is, for example, not split if you have two lines, and if the Galois group maps them, if they are only defined over a field extension, that would be something what is not split. And fibers which are not split are sort of the bad fibers, and the number or the extent to what we have bad fibers that influences the complexity of that problem. Typically, the rank of the vibration f is defined as you take the sum of the degrees of all closed points. I will give an example in a moment of P1, such that the fiber above this thing is not split. So a typical example to which one wants to apply these things is compactifications or smooth compactifications of the following variety. You take some polynomial in one variable and set it equal to the norm of, say, an extension. Take the norm of an extension of your little field little k. Say you have omega 1 up to omega n, a k basis of your number field k, and then you take a combination x1 omega 1, split it, an element in the field extension capital K into its coordinate with respect to the little k basis. It's a typical norm form. And yeah, so you look at this variety and smooth compactifications of it, and this would be typical examples that you could apply these theorems to. So here you would take this variety and fiber it over this variable t. And if the polynomial p of t is not equal to 0, then what you find here is something, well, a non-zero constant is equal to a norm form, and that's a smooth fiber. So all of them are good. So the bad fibers lie over places where you have zeros of your polynomial p of t, or the place where you compactify the infinity. And this is a very nice family here, because the smooth fibers, or for example the fibers where you have here a non-zero constant, they satisfy Collier-Toulin's conjecture, because these fibers are of the form norm form equals constant, so they are homogeneous spaces under norm 1 tori, and they are known to satisfy Collier-Toulin's conjecture. And sort of the way you can imagine this sort of, I mean, this p of t has a bunch of zeros, and so it splits into some irreducible polynomials, and each such irreducible polynomial gives you a closed point at which you have a non-split fiber. And this would correspond then to the rank of f. So the sum of these degrees. So the higher I take the degree of p, sort of the higher your rank gets, no more complicated. So this is just give an indication for how, yeah, one way how one hopes maybe to measure the complexity of this problem. So such vibration theorems, they are holds for low rank, for small rank. So it holds for the case that a rank of f is equal to 1. That's a work of David Harari. I think, I mean, you may correct me, 1994 and 91, around that time.
Maybe 97.
Oh, sorry, then I couldn't read my handwriting. Thank you. I was just thinking the one. Thank you. If the rank of f is equal to 2, and if the fibers, if they satisfy weak approximation, then there's some work of Collier-Toulin and Skorobogatov, who verify then such a vibration theorem. And this has been later extended by Harpers and Wittenberg to general case. So the main statement that I want to talk about is a result of Harpers and Wittenberg, who figured out that you can prove such a vibration statement A if you assume a conjecture on split values of polynomials. So in a groundbreaking work, I guess it's fair to say, Harpers and Wittenberg in 2015 showed that A holds under the assumption of the following conjecture. So this conjecture is conjecture called on split values of polynomials, because this is what all of then these analytics results are going to build on. I want to state a conjecture actually in its genuine form. It looks a bit technical, but because this is for us a starting point of a number of investigations, I want to take the time to actually state it. And I will explain after why it's called a conjecture on split values of polynomials. So we start with little k, our number field. And let's say n is some natural number, at least one, that more or less corresponds to the number of factors in the polynomial p of t plus 1, maybe. So it's a number of sort of, bad sort of the polynomials, bad closed points. And each of them, say, is described by some polynomial. So I take p1 of t up to pn of t in kt, pairwise distinct, irreducible, monic polynomials. You assume that they are irreducible, as otherwise you would split them into just two different polynomials and throw all of them into your list. So in this example, you can just think of factor p as a product of pn's, and okay, there's a little lie behind it because of the compactification. There's one added. And each of them defines me a field extension, little ki, which is k giant t mod quotient outwards pi of t. This is actually now a field because I assumed pi to be irreducible. So, and I want to write for ai, that's the class of t in little ki. This little ai is a 0 of p. And then you take finite extensions of all of these fields, little ki. If you want, you can assume that they are Galois, but finite is also fine. And you take some elements bi, which are invertible, which live in ki. So for each of these polynomials, I take another field extension li and an element bi. What we eventually more or less want to do is we want to find a value of t such that each of these polynomials takes values which are more or less completely split in the extension li, if it were Galois. But formally, we also want to approximate t at a number of fixed places. It's a bit like if you work with weak approximation, then you have a number of fixed places where you want to approximate something. So that's now a little bit of technical mess here, but just write it down. In the set omega k of all places, you take a subset, say S, of some exceptional places where you want to have some approximation property, and that contains a bunch of, say, all real places of k, places above which some bi is not a unit, or places above which some li over ki is ramified. So you throw in sort of for small places, and then you choose some values of t sub v in kv for all v in the set of exceptional places, and then you want to find a value capital little t which then approximates these tvs. But you assume that these tvs are chosen in a nice way. If you want for a first reading, you can assume the following, can ignore the following assumption. You can say a bit about it later. You want that for all such exceptional places in all i's, the values bi times tv minus ai are local norms. Local norms in the sense of if you take li tensor with any kv, so v is a place of little k, take the norm down to kv. So I want that there is xiv in li tensor over k with kv star, such that locally you are a norm in ki tensor with kv. So this all splits into products. I mean, this thing is a product of local places of ki, and then you take respectively all of the local norms. All of the tv minus a should be local norms. And so then I can finish this here. Then the statement is, then you claim that there is some element t0 in k, such that first of all, T0 approximates your local TVs arbitrarily well, is arbitrarily close to say TV for all V in S. And the second, the sort of key statement here is that for all I, so for all each of these polynomials, I between 1 and n, and for all omega, which is a finite place of the field extension little ki, if the valuation of t sub 0 minus ai is positive, then omega lies above. So it's either exceptional, a place in S, or if it's not exceptional, you want that Li possesses a place of degree 1 over little omega. Okay, so that's the conjecture. Maybe let's look just at an example for a moment to illustrate what this means. So for now, maybe if you want, forget about the local assumptions in between here. The case that I will discuss actually in the second part is the one where all of the polynomials pi are linear polynomials. So if they're all linear polynomials, then all your little ki's are all just k. Say the ground field, imagine it's the rational numbers. Then we are talking about a bunch of linear polynomials over the rational numbers. And then this t0 minus ai, that's just my linear polynomial, essentially. So then I want that I have a bunch of linear polynomials, and say L, they are all equal to, say, Q adjoint I. It's a field extension of Q. Then I want that if my linear polynomial has a positive valuation, then at this place where it has a positive valuation, this prime is completely split in Q adjoint I. Which would mean that if I have a linear polynomial and I have a positive p-adic valuation, then this p is congruent to 1 modulo 4. So, for example, this would hold if you could make all your linear forms equal to products of primes which are congruent 1 modulo 4. Then this would correspond to the case that we have all these Li's as Q adjoint I, and then they would be completely split. More generally, if you have a Galois extension, this boils down to saying that you want to find a value t such that these values pi of t take completely split values in the field extensions Li. So you're saying something about the prime factors of them. Maybe I can. This one? Yes. Maybe I could remark that what I already said a little bit. So where do these pi's come from? So if you fix, say, some data x and f in this vibrations theorem A, then in order to prove such a vibrations theorem, you need this conjecture 2 for polynomials pi of t such that the zeros of pi of t for all of them, such they contain all non-split fibers of f. So before one had this conjecture on split values of polynomial, in vibration theorems, people made use of Schindler's hypothesis in place of this. And I want to give Schindler's hypothesis just as is there a question? No.
I'm confused. What did you write?
Oh, I was trying to say this is more maybe not entirely precise remark. It's if you fix some nice variety X with a dominant fiber down to P1, with a dominant morphism F, then if you want to prove this theorem A of vibration statement, then you need this conjecture for a bunch of polynomials which zero set contains all the places, all the points above which you have non-split fibers. So try to indicate how you move from the vibration theorem to what polynomials you need in the end. It's just not so important here. So in comparison, I want to state Schindler's hypothesis. Let's call this thing H. So that's been something what has previously been used in place of this conjecture on split values of polynomials, and which applies it in some cases. I don't state it now with all the technical details, just a statement in a form like, say, P1 up to Pn of t, say, with integer coefficients, irreducible polynomials with positive leading coefficients such that a product of P of I of t has no fixed prime divisor What I mean with that I don't have a fixed prime divisor is that if you have this product of polynomials and you let t average over all, look at all the integers, then there's not a fixed prime like 5 such that 5 always divides this product. If this would happen, then if I want to make all of them prime, I would always force one of them to be equal to this fixed prime. So this is a reasonable assumption to assume then, hope then that there are infinitely many values t in the integers such that each of the pi of t is prime for all I. I think now I need a new fastboard. So why have I written now Schindler's hypothesis as comparison on the blackboard? Well, the reason is that you can show that in the case that these LIs are abelian extensions, then Schindler's hypothesis implies this hypothesis in split values of polynomials. And this is a proposition which is also due to Harpers and Wittenberg, which says that if all Li over this Ki, if there are abelian, or there's actually the notion of almost abelian if you want, in conjecture 2. So if you look at a case of conjecture 2 where these are, say, abelian field extensions, then Schindler's hypothesis, H, implies this conjecture on split values of polynomials. And this uses the reciprocity law in global class field theory. You want to make something split, and if you know it's prime, then if you're okay at all places, you can't be not split at only one. So the remark that I want to make is that the great achievement in this work of Harpers and Wittenberg is to move away from Schindler's hypothesis to this new conjecture on split values of polynomials. Because Schindler's hypothesis is very useful for vibration theorems, but it's hopelessly difficult. And I just want to indicate sort of how hopeless sort of this seems. Maybe it's even an understatement if I say it's very hard. For example, if you look at Schindler's hypothesis, only one polynomial of degree 2, then this is a very deep open problem. So we don't even know if, say, the polynomial t squared plus 1, so this is now one polynomial of degree 2, if this is infinitely often prime. We conjecture to be so. This is Landau's conjecture, and it's completely open. It also includes the twin prime conjecture. For example, you could take the two polynomials, one polynomial t and the other polynomial t plus 2. It's not two linear polynomials, and they're both irreducible. There's no fixed prime divisor. So we conjecture that there are infinitely many values such that both of them are prime. But that's saying we have infinitely many twin primes. It's also hopelessly hard. And sort of the simplest case in Schindler's hypothesis that you can think about would be like one polynomial which is linear. Well, and this reduces to the statement that there are infinitely many primes in arithmetic progressions. So this reduces. Yeah.
Is there a valid condition on S being finite in this conjecture?
Oh yes, I meant this to be finite. Thank you. Yes, I should write it somewhere. So thank you for asking. Yes, just forget this. Yes, of course. Yeah. So we have now this nice conjecture, and there are now different ways to approach this conjecture. So the last talk on Friday, we will directly look at some approach to theoretically approach this thing. But Habers and Wittenberg figured out that there is some way to reduce the problem, this split values conjecture, to a problem of proving strong approximation for some auxiliary variety. And that's the approach that I first want to talk about, because then we now reduce to a problem of actually finding some rational points or integral points somewhere. I don't want to state the auxiliary variety in all of its generality, because I feel like this is now technically enough sort of details. So the next two lines are a bit vague, and then we'll get a bit more precise again. So Habers and Wittenberg show they introduce some auxiliary variety. It's some of affine variety, and we will see it in some examples. So you can introduce some auxiliary variety, say W, with the property that if you can prove strong approximation of any finite place for W, then you imply this conjecture on split values of polynomials. So this depending on all your data, like the polynomials pi of t and these field extensions Li over Ki, the choices of Bi that you made, such that the following holds. If W satisfies strong approximation of any finite place, then the conjecture 2 holds for this set of data that we've chosen for these polynomials pi of t, Li over Ki, and say Bi. The strong approximation is a bit of a, it's a notion for affine varieties. Maybe I can put this here. W, an affine variety, satisfies a strong approximation of a finite set of places T if the K rational points of this thing is dense in the restricted product omega of a the adults away from T. So this is the restricted product of W of KV where Li does not live in T. So you ignore a couple of places, And then you want to produce a point which approximates some primes a certain point, and apart from that is integral. That's more or less a statement of strong approximation. But so the key is there is this auxiliary variety, and if you can prove strong approximation of any place, then you can prove this conjecture.
The last line in the first blackboard, P1 is linear, reduces to infinity many primes in what is APN?
Arithmetic progressions. And this is a 1, so I'm trying to make the case that if you only have one linear polynomial, and if this is, yeah.
And in the right hand, what does no fixed
yes. So this thing here means that there exists some value that for all primes p, there's some value in the integers such that p does not divide the product of pi of t. Thank you. Okay, so I will not state I will not tell you what this variety W looks in the general case, but I want to tell you what it looks like in the first case that we are now interested in, which is that all of these little ki's are linear, where all of these polynomials pi are linear. And that I want to state, actually. And I write it here because I hope that you can kind of get a bit of a sense of why producing a point in W will solve this conjecture. Maybe not formally, but I hope that the connection will be a bit clearer then. So here is the statement of what does this auxiliary variety look like. So this auxiliary variety, which I want to call W, in the case that, say, k is the rational numbers, and all of these little k's are the rational numbers, that they are all q is equivalent to saying that my polynomials are linear. And now we still have some field extensions. Now Li, they are now number fields. If you want, you can make them Galois and say they have a degree di. I formulate this already now in a way that it gets close to counting and makes it counting easier. I want to describe actually essentially what a norm form looks like. So I want to choose now a set basis of the ring of integers in Li. This thing has a set basis. We want to give this thing a name. Say omega 1. This I here denotes that I'm talking about the i's, the Li. This is i's field extension. And this thing has degree di, so I have a di dimensional basis. This is my set basis of the ring of integers. And then, oh, that's fine. I want to introduce the notation if I write xi, and if I underline it, then I mean a tuple of variables with this thing. Then I mean a tuple of xi1 up to xi. It's a di dimensional tuple xi di. So I'm doing that because I want to talk about an element, say in Li, and I want to break it down via the basis omega I into, well, data of rational numbers. And then we want to set that the norm Li of this xi is equal then to the norm from the field Li down to q of the sum of xi j omega ji, where j runs from 1 up to di. So this is how you can define a norm form. So you should think about maybe these xij rational numbers, and then each set of rational numbers gives me a unique number in the number field Li, an element in Li, and then I take the norm down to it. But I break it down into the basis, so it's like taking explicitly a while restriction, more or less, what I'm happening here. But I want to formulate it in that way because we now want to count points over the integers. So that's why I introduce here this basis of the integers. Because if I now stick in here for the xij integers, then if you take the norm, it's going to be an integer. It's going to be integral. That's why we like to have a basis of the integers. So this thing is now, if you view it in these variables xij, this is now a homogeneous polynomial of degree di in di variables with integer coefficients. That's now a nice and concrete object. Now, now I want to take linear forms Li. They depend now on lambda and mu. And I want to set them equal to bi times lambda minus ai mu. So these a's and b's are these a's and b's floating around in this conjecture over here. And after a change of variables, again to make everything nice and countable later on, I want to assume that I have now integer coefficients. I mean, a priori, ai and bi are rational numbers, so it's rational linear forms, but I want to change the way these denominators to end up with something with integer coefficients. So where is this lambda and, okay, that's fine, I guess. And now this auxiliary variety can be interpreted. One can interpret this auxiliary variety W as a subvariety of affine space of dimension d1 plus dn plus 2 as an open subset, a subvariety of the following variety, given by the system of norm form Li over Q of xi is equal to your linear form Li of lambda and mu. And this say be non-zero for I between 1 and n. And I furthermore want to restrict this to some open subset such that if you think about these norm forms over extension Li, they split into a product of linear things. And I want to exclude the set where two of the linear factors vanish. So I want to make this and such that no two linear factors of a norm form Li or Q from xi vanish. That's fine. So why has this now something to do with this conjecture? So if we say go back to this case that Li is Q adjoint I, then I have here sums of two squares. And then we want to make all these linear forms equal to sums of two squares. The condition that there's no linear factor, that no two linear factors vanishes, means that if I have a linear form, it's divisible by some prime number p, then this prime number p has to be completely split in Q adjoint I. It's be congruent 1 modulo 4. The way that one proves this strong approximation result, in fact, is like you show that there are numbers lambda and mu, such that these Li's are all square free, and such that they are norms. If you're square free and a norm, well then all the primes have to be completely split in these extensions Li. So this is a bit where this relation comes from. So indeed one can now prove that strong approximation of a finite place holds for this variety, but I want to talk about some weaker result to make it a bit simpler, which is to show that weak approximation for W holds. Before we move on, one remark. These linear forms that we constructed have the property that no two of these linear forms are linearly dependent. This is going to be very important later, so I just want to state this for now. No two of the linear forms Li of lambda mu are linearly dependent. And that comes from, so when could those two be linearly independent? Well, it would mean that AI and HJ, they have to be the same for some I and J, but that's what we excluded. If AI is not equal to HJ for I is not equal to J. And this comes from the assumption in the split value conjecture that your polynomials are all pairwise distinct. So if we start as pairwise distinct linear forms, then also here we have linearly independent forms. And it's now kind of relatively simple to see, but it's going to be very important later on. That's why I write this down here. So first of all, there is a theorem which is due to Lilian Matthiessen, maybe 2016 around that time. And she shows that W satisfies a strong approximation of infinity of one place. So she kind of proves the statement, which then leads to the proof of this conjecture on split values of polynomials. But as I said, I want to talk about something slightly easier to explain, theorem 4 here, which is an earlier work of Browning and Matthiessen.
Sorry, on this board you said of any finite place, infinity.
Sorry. Yeah, it doesn't need to be finite, I believe. Finite set, yes. Yeah, finite non-empty.
You mean infinite place?
Yes, non-empty finite set. I think that should be good. Of places, then conjecture. So, so we have a resultant strong approximation. So the weaker statement would be that W satisfies the Hasse principle and weak approximation. Yeah, I'm just thinking, I believe that you need to include an infinite place for this statement because, but again, yeah. So the point I want to make is I want to talk about a slightly weaker statement, which is actually already very interesting, in which you see in terms of the time it arose before the conjecture and before the resultant strong approximation. And one reason is that you can also come to this statement that realizing that this is important. Yeah.
So that's W in the specific case.
Yes. W is not this W. Thank you. Yes. So on this board, W is this linear thing. Yes. It arises also via descent from some problems. So maybe I can write this down here. Theorem 4 already implies, it's not strong enough to imply all these nice vibration theorems that I wanted, but in specific cases you can also already apply to some interesting examples. So theorem 4 example implies that via descent, that's where it pops up, any smooth projective model of variety, which we have seen before, like you take some norm form, norm of x equal to a product of a polynomial which splits into a bunch of linear factors. Say if you want, okay. Can also have exponents. I1 to n with the EI rational numbers, pairwise distinct, and MI positive. Okay, I don't even need to assume that they are pairwise distinct. You just put them into the polynomial in the MIs. C, rational number, that this satisfies Collier-Tillene's conjecture. So if you look at a specific variety x, then again it comes with some vibration down to this variable t, and above each t you have norm, torus, and norm 1, torus, and in order to prove Collier-Tillene's conjecture for smooth projective models of this thing, in place of applying the vibration method, you can also apply descent methods, like Alexei was involved in many of these articles. And then you can reduce the problem of proving Collier-Tillene's conjecture for this variety to showing that weak approximation holds for this auxiliary variety. So there's an independent reason why you might be interested in weak approximation for W. Although it doesn't imply the complete conjecture, it already implies some nice statement for this variety. So I want to justify that talking about weak approximation for W is an interesting problem on its own. And now I want to use the rest of the time to explain how to make a counting problem out of this problem of showing weak approximation for this variety W, which is up there on the blackboard. Okay, so in the next maybe 16 minutes, I will try to show how to move from this statement to a counting problem. I mean, in a way, Emmanuel was already talking about how counting is important for showing weak approximation. I mean, he was discussing Birch's theorem. And in order to show weak approximation for such a hypersurface, what you do is you count points. You show that there are many points. And all of these analytic approaches that I'm talking about today, tomorrow, and on Friday, all of them aim at essentially proving weak approximation for some variety or producing some points. And in each case, we will not just produce one point, but we will kind of make a counting problem out of it and then show that there are sort of infinitely many points, that there's a large density of points. I mean, none of them will be constructive, but yeah, all of them will give you sort of a statement on density of points, actually. So now let's talk about a reduction of theorem 4 to a counting problem. And the process, what I'm doing now, is no way unique. What I mean is like how to make out of this some problem where you can count things. There's now many ways to do that. And now I'm starting to choose one path which leads us into a formulation which you can attack with methods from additive combinatorics. There's other ways that you could decide to count points in there, which give you a different angle of different viewpoint. But now I choose a way to formulate this to force this into something additive combinatorics looking like. Okay, so what do we even want to count? So we want to show weak approximation. So more or less this boils down to you want to find integer points. First of all, you want to produce a point. You want to show the Hasse principles here holds. You want to produce a point on this variety here. You want to find integer solutions in these vectors xi, lambda, and mu. And this weak approximation property means that you want to be able to approximate lambda, mu, and xi at some number of finite places, which comes down to some concurrence restrictions. And then you want to find some integer point in there. So the way that I now want to view this problem is, let's imagine we vary over lambda and mu. We put in their integer vectors. And then we ask, when are all of these linear forms equal to some norm form? So for that, I want to imagine we have some number here, number m, and then I want to ask, when is a number m equal to a norm form? For that, we introduce our representation function. So define for some integer m, so in set, say not equal to 0, a function Ri of m. I will give the definition sort of while explaining this. We want to count how often can you write m as a norm from Li down to q of a vector xi. And we would also like to make sure that maybe this vector xi is in a certain, all of these variables xi are congruent to say bi modulo m. I will put something here in a moment. So you want to choose some module m, say positive, and a set of residue classes bi in set modulo m set to the power di. And then we want to count how often is m equal to this norm where x is in a certain residue class. And well, if I write it down like that, so xi I'm thinking of as an integer vector, so it's di-dimensional. If I write it down like that, and this is typically an infinite thing, if it is non-empty, because if you can represent m by some norm, then it sort of more or less means m is equal to the norm of some element in the ring of integers of Li. But if you have a non-trivial unit group, not rank 0, say, then you suddenly would get infinitely many solutions. You could multiply this element xi with some unit of norm plus 1, and then you are still a solution. So to make out of this a finite counting process, there are different ways. Something that works very nicely is that you look at some fundamental domain, which I now call xi, of the positive unit action, and you restrict to this fundamental domain. So here I'm a bit vague for time reasons, but it's not a most important point. So if I want, I'm happy to explain later how to do this. But so you would choose in di-dimensional space some suitable. It can be even part of a suitable fundamental domain. Of the positive unit action. There's also other ways to make this finite. I could also decide to, say, truncate all of these variables xi. I could also say I choose, say, some large parameter, whatever, or p, and I want all of these variables xi to be bounded. That's also a way to make this a finite problem, but this is a bit nicer to work with because then my counting function is sort of only depends on m now in this data bi and m and my choice of a fundamental domain. But so the point is we construct some function which detects if a number is a norm. And if yes, then it counts it with some multiplicity. Covering the conjectures, we now focus on the problem of finding points in this variety. So as I said, the way I want to think about this is in finding points here, I want to average lambda and mu over some region, and then I want to check, do I ever hit a point where all these linear forms are norms? So I now need to introduce, and I now need to tell you sort of what's the area of lambdas and mu's that we are looking for. What do we try to count? So for that, I want to start with some convex set in the plane R2 for the lambda and mu's. And then you choose some large number, and then you blow up this convex domain, and then you ask for integer points in this blown up area of your convex domain. So let's say k in R2 be a bounded convex set. And I want to make it small for some technical reasons. So this is, you can ignore really if you want. Formally, I would like that all the linear forms on my convex set are always bounded by 1. Doesn't really matter because we are bounded, so otherwise you just have another constant. You scale things a little bit down. And the goal now is, and furthermore I want to fix some vector A. So M was this module to what we want to approximate everything at. And now I also want to make sure that lambda and mu live in given residue classes modulo capital M. This is detected by some choice of A that we make. And now the goal is to study the counting function say n of capital T. T is now a new parameter. And now we want to count all tuples u. Oh, this was called lambda and mu before, so let's call them lambda and mu again. I want to count all tuples lambda and mu, integers, which are of size t, which is t times the bounded set k, and such that lambda and mu are each congruent to, say, A1 or A2, modulo M. And then we look for each such choice of lambda and mu at a linear form lambda and mu, and then we test, is this linear form now represented by a norm form? And you want simultaneously that all of the linear forms are represented by a norm form, so we take the product over all of these indicator functions from I up to n. Now the key is that if this counting function nt is positive, then this means that we count at least one tuple of lambda and mu's, which are integers, which are in the right residue class, for which all of these functions Ri have to be positive, which means that we find a tuple of lambda and mu such that simultaneously each of the linear forms Li has to be represented by some norm from the field extension Li. This will produce a point on this variety here. So it would mean we have found a combination of lambda and mu such that each of the Li's, this thing has a solution. And we even counted them with multiplicity. And so this is why if we can make this non-zero, then we have shown weak approximation for this original variety. So now I want to compare this to something that maybe you've seen before, somewhere floating around. So that's the motivation of why you want to put it into this shape, more or less. So now I want to compare with correlations of, say, the von Mangold function, lambda of n. So the von Mangold function says is equal to logarithm of p if n is equal to a prime power and is 0 otherwise. So it's a weighted prime indicator function. Now let's compare it to a correlation, say, of we take lambda and mu. And now forget about the concurrence restriction, it's more technical detail. Let's count lambda and mu in set 2 intersected with some area and take the product I to n of the von Mangold function. Now let's choose linear forms of the form, say, lambda plus I minus 1 times mu. So I choose the linear forms lambda, lambda plus mu, lambda plus 2 mu, lambda plus 3 mu, and so on. These are all linearly independent forms in lambda and mu. And if you now look at this object, then it looks very, very similar to our object n of t. All what we did is I specialized to some functions, and I replaced this norm counting function with the von Mangold function. And what does this object do here? Well, this thing counts arithmetic progressions in the primes. So this thing counts n-term arithmetic progressions. in the primes, or prime powers to be precise. This is a breakthrough result which was solved 2008 or even the years before by Green and Tao. In say 2008, in their work where they established that the primes contain arbitrarily long arithmetic progressions. That's how they established this result. Because these linear forms, the linear forms that we look at is lambda plus mu, is lambda plus 2 mu, and up to lambda plus n minus 1 times mu. And the pattern of this form is called an n-term arithmetic progression. So if you can now play the same game with this counting function, and you choose t large, and if you make sure this is positive, this counting function, it means that you have found values of lambda and mu, such that each of these linear forms is a prime or prime power. So that's how you produce infinitely many arbitrary long arithmetic progressions in the primes. I'm writing this here because the techniques used for this counting function n of t really build upon this strategy that Green and Tao developed. So they kind of follow this approach, and that's why I wanted to make a point of why you want to formulate this into a correlation problem. If I have 1 minute left, excellent. If I have 1 minute left, then I can now just take it to state a theorem on this counting function n of t. So in practice, a theorem that is due to Browning and Mathématiques, which is sort of the counting statement of weak approximation, says that you can asymptotically evaluate n of t in the same way that Green and Tao managed to evaluate this function of the von Mangold function. And n of t then is equal to a product of local densities, beta p, so this is all some real numbers, some constant times t to the power s, plus an error term little o of t to the power s. So for t going to infinity, this is much smaller than the main term. This holds for t going to infinity. And this product of the p's, that's a product of local densities which is absolutely convergent. And it's an absolutely convergent product of local densities. These local densities are kind of similar to what you see in this work of Birch that Emmanuel was talking about. I don't have the time now to write them down, but each of these local density measures at a prime p if your variety over there has enough p-adic points. So in that sense, this gives you a local global principle from an analytic point of view that if you want to produce a point here, you need to make sure this leading constant is positive. And for that, you need to make sure every of these beta p's is positive. And every such local density is positive if you have enough p-adic points. I think that's enough before the chairman tells me that I'm over time, which I am probably. Sorry about that. So we'll continue, I think, tomorrow. And then I want to indicate a bit about what is going into this type of theorem. Thank you.